So hello everyone. I am Dhanya. So I'll be covering Introduction to Risk 5, the first part of the last unit. So Risk 5 architecture. So I'll be starting with the first part, followed by Srinizi, Nagadarshan, Angel and Harish, and maybe Dia also. So I'll start with my part, Introduction to Risk 5 architecture. So my part, I'll mostly be trying to cover the motivation behind why we are learning risk 5. So that is going to be something that I'll focus on. So why do we need risk 5? Why did we start from CISC? Why did we think that it is not as good as it is? And why did we end up landing on risk 5 architecture is something that we're going to look into. So firstly, I'd like to ask, like, what exactly is a processor? Okay. So processor is essentially the brain of the computer, no? It takes input, it processes, and then it gives some output. So every application, say like calculator, camera, whatever, okay. So it requires processor to execute instructions, no? So, but do you think processors actually understand languages like C, Python, or Java directly? Like, do you think they understand it directly? No, right? So let's say this, just take an example, no? Like say, let's take A is equal to B plus C plus D. So the compiler just like processes this complex instruction and it brings to like the instruction set architecture, like add T naught is comma S1 comma S2, add S naught comma T naught comma S3. So then this also is like converted to zeros and ones, which the machine language with the computer actually understands, or which the machine actually understands. No. So they only understands the machine language. So this from our complex instruction, we need to bring it as close to us to the hardware, right? So that is our instruction set architecture. So from our complex code that we have, we try to like have find an interface between the hardware and the software level. So that is our instruction set architecture or the ISA that we are talking about. So I hope you got like a basic essence of what an ISA is. Okay. So what does ISA deal with? So it defines the processor operations, it specifies data handling, and it governs software and hardware interaction. So it also tells about how memories are accessed and what registers are exactly available and how software communicates with the CPU and so on. Okay, so it acts as an interface between between the software and the hardware. Okay, so ISA defines the complete behavior of a computing system at the instruction level. So just an example for it, like for processing data, ISA provides instruction to process decimal numbers. So that exactly uses our IEEE 75754 representation. I mean, just a point I wanted to cover. But one sorry. Okay. So moving forward, I think it's essential that we start with the evolution of how everything began. So initially around pre 1970s, so memory was very expensive and the RAM was also very scarce. Okay, so RAM was scarce and very costly. So architect actually crammed as much work as possible into a single instruction to save memory. So if memory is so less, what would you think as an architect? You would try to like compress everything into a very small instruction so that you efficiently use your memory. So that is what that is how CISC actually naturally came into picture. Like CISC is not actually, it was not actually bad. For that era, it was the right thing to do. Like you didn't have memory. So what could you do? You just try to cramp everything. You try to reduce your instructions and then you end up using your memory efficiently. Right. That is what CISC is also. So one instruction could fetch data, load registers, compute, and store results all at once. So x86 is like a dominant survivor of it also uses CISC architecture. It's a dominant survivor of the era, and it's used in like PCs and servers today. So the idea behind this CISC was that it's do more with one instruction. Okay, but there is hardware complexity because if you're having very complex instruction, at the end of the day, a compiler is going to take up the whole load of understanding what the instruction is, that complex instruction is. So that is what CISC is, no? So we started with, if you had to look at the flow chart here, memory was low and expensive. So we need to bridge the gap between high level and low level languages. So that's why we came up with CISC. So x86 is a dominant survivor used in PCs and servers, large, powerful, but inefficient. Why did it become inefficient is something that we look into soon. And then single instruction performs high level and low level language, low level processes. So next up, so if you see, researchers know like around 1980s, what did they find was that even though the CISC and all existed, the first thing that they noticed was that only the simple instructions dominated, as in your assignment operators, your loops, your branch statements, your comparison operators. Only these four kept dominating. So, and then the second thing that they noticed was that the operands were localized. Okay, so most memory references were to just the local variables, your function parameters, and the recently used values. Only the recently used functions and the values. Okay, so the operands were localized. And the third point was that the procedural calls were expensive. So the function calls and the return statements, the repeated function calls, all were very expensive. So at the end of the day, uh, many complex instructions were rarely used. Okay, so that's when there came something called as ARM. Because what was the question? Why make hardware complicated for instructions that are rarely used? Valid, right? Like if it's not even used, then why make your hardware that much complicated? Why do all of this? So that's when ARM architecture came into picture. So 80% of the execution spent on 20% of the instructions. So risk ideal motive is to like keep the instructions simple and let the compiler handle the rest. Okay, so ARM focuses on power efficiency and battery power devices, majorly used in like mobile and embedded devices. Okay, so yeah, risk entire motive is simplicity over complexity. So that is the entire motive behind ARM architectures, which uses risk. So risk majorly focuses on simple instructions, smaller instruction set, easier pipelining, of course, uh, and then faster execution. So this is what the risk focuses on left. But one thing that's a con for ARM architecture, which follows risk, is that it has proprietary licensing. So you need to pay for it to actually access and use it. Okay, so that it has the intellectual property. So I mean that's one of the cons if I had to point it out. So in general, so in general, how risk works? If I had to ask you how risk works, then it would just be upon three principles. The first would be simple instructions. Everything happens in just one clock cycle. So that would be the first point. The second point would be it uses load and store architecture. Correct? No. So we just talked about how 80% of the execution spent on only 20% of the instructions. So most of the statement like instructions were all waste. Okay. So load and load and store architecture essentially means that only load and store are used, that and it is used for every and any statement, and makes the instruction set less complicated. Okay, so then we also try to use as many registers as possible, because I mean the access time for registers is much more faster. No, if you see RAM and all, it is obviously slower than even your cache. It is faster, but registers are even more faster. So we try to increase the number of registers in our risk architecture. And of course, the third principle would be efficient pipelining. So we've learned a whole chapter on it, pipelining. So risk does make it efficient pipelining, since everything is ideally expected to happen in one clock cycle. Okay, so so next, if I had to tell about the risk and the risk 5 architecture. So we'll just come back to this in just 2 minutes, but I just want to like just talk about one or two things. So because when I was studying this, I just got one or two doubts, because while we are doing cache mapping, like in memory management, we were actually talking about cache, right? So the one thing that we dealt about was that when cache uh, when cache like repeatedly gets updated by values, how do we ensure that those values are updated in the RAM also? That was one point of question that we discussed in the memory chapter. So I was wondering, if we are using so many registers in our risk architecture, then like how does the same thing work here? Like because in registers it gets updated even more, even like more than your cache also, right? So I mean, it could happen that way also. Your registers could get updated regularly, So how are we ensuring that the data is preserved properly, and ensuring that it is actually saved in the RAM properly or not? Because we can't do it every single time. So that will be like it would take up a lot of time also. So I mean, like slightly out of context, but I just looked up on it, so I'll just try to cover. Um, so there's something called as the hardware method and the software method. So hardware method is essentially that, so the risk processes, no, they use many registers, as you all know. So these registers are divided into register windows. Okay, so each function in our program, they get one register window. So each function gets one register window. Okay, so there are two pointers. So there's current window pointer, CWP, and saved window pointer. So this current window pointer will point to the register window that is recently used, like the function that is recently activated or recently used or recently accessed. And then the saved window pointer, no, it will point uh, to the older window that was actually sent back to the RAM, like the last thing that was sent back to the RAM because there was not enough space. Okay, so essentially, if a new function is called, then the current window will now point to the new function. Current window, it will point to the current function that is being accessed. Then, if all the windows were occupied, then the older window will get spilled to the RAM. Okay, so that will be taken care by the saved window pointer. Okay, so this is what I looked into this is what the hardware approaches that I looked into. And then there's another software method that is something that's relatable for us also, which uses graph coloring. Okay, so the idea behind this is that the compilers like assumes there are unlimited registers. They don't know that there are only these many registers and all. So compilers, they always assume that there's like unlimited registers, and they gives temporary registers. Okay, so each so essentially, like how it happens is that each variable like becomes a node. Okay, so each variable becomes a node. So if, let's say, if two variables are active at the same time, then an edge is drawn between them. So if they're both active at the same time, then they can't have a same color. No, that's why there's an edge drawn between them. So same graph color technique only that we studied for discrete math also. So they cannot essentially share the same register. So if it's a different color, like if they have an edge between them, and if there's a different color for them, then they cannot share the same registers. But if it's the same color, then they can obviously share the same register. Okay, so this is the idea behind it. So if there are like n registers, so compiler needs to like color using n colors. Okay, so if there are n nodes and like n registers, so you need to color n you need n colors to color. So if you don't have enough space, then you like push your older variable to your main memory. Okay, so this is how essentially it works. So I was just like thought that it would be interesting to share this, so that's why I shared. So otherwise, okay, moving on. So we just talked about CISC, right? How it was being complex, and how initially we had the memory was very less, so we needed to have very compact and complex instructions. But how did it change? I mean, did we magically get all of the memory back? Like, did we get memory everything back? So that's what. Okay, so essentially, what does Moore's law say is that so the transistor count on the on the chips, no? So it roughly doubles every few years. That's what Moore's law said. So it did prove true, and it is still proving true all these years. So because of this, the memory we had enough memory to actually store more instructions. So that's why we ended up in the RISC architecture. So now we have good enough memory to store more instructions. So and we use simple fixed length instruction executed in one clock cycle that enables pipelining. So compilers handle the extra work. So and then this part, the RV332 IEA and the extensions like FMV, all of this will be covered by Srinidhi and like many others to come. So if you had to just know, it's M is for a notation for multiply, F is for float, V is for vector, and so on. So yeah, so I told you the con was that proprietary licensing, but RISC-V is all open source. Okay, so anyone and everyone can use it. So there's no licensing fee. And then it's used in Google TPUs, sci-fi cores, NASA spacecraft, and even I think Airtel's 5G also. So yeah, I think, and then nowadays it's used in AI accelerators, IoT devices, and custom processes. So yeah, that's what I wanted to cover essentially. So from based on the session, I think it would be better for you to think in terms of what the trade-off between CISC and RISC was and why RISC has an upper hand. So just maybe run over the session and like try to think of this answer. So that's about it. So the last question is that does the distinction between CISC and RISC actually matter nowadays? So the actual fact is that many modern x86 architectures, no, I mean x86 is CISC architectures, no. So they actually those instructions are broken down like RISC-like like RISC-like instructions. Okay, so these x86 instructions are also like broken down like, and it is trying to imitate or imitate how a risk would work like. So essentially in the modern world everything is just mixed up. So all of risk advantages and CISC advantages taken up and it's mixed up, and it's mixed up and it's used. So yeah, this would be the answer to this question. Otherwise, I would like you to think about what the answer could be to for this question. I think I would have just covered it entirely throughout the session. You can just try to recollect the points. Um, so I hope you understood what I tried to convey and you understood why we ended up in risk, the motivation behind learning risk is. So yeah, and references would be the official Risk 5 website and then William Starling's computer organization and architecture textbook. It's it's pretty detailed. So if you have want to refer to it, just maybe refer to only like first few pages. Otherwise, it just goes to too many complications. So yeah, thank you so much. I hope you understood. Thank you.
Brief overview on the different extensions of RISC-V architecture. So before moving on, let's look at the features. RISC-V is open source and completely free to use, essentially, unlike your x86 or ARM processors which are in your computers, which charge a licensing fee. And it gives you so much more freedom because you only have the base ISA, and depending on what your needs are and requirements of the projects or domain, you add on the instructions you need with extensions. All the specifications and how RISC-V works, every detail of all extensions, the opcode, etc., is available in the RISC-V International website. So let's move on to the base ISAs. These are not just random numbers or letters put together, they have some meaning behind it. So RV stands for RISC-V, and the number followed immediately after is the size of the registers. So here it's 32 bits, 64 bits, 32 bits again, but I'll come to this later. and 128 bits. This version is being very recently developed. For now, we know this so far. And what it's saying is, usually base ICs have 32 registers, right? So it's saying I have 32-bit sized 32 registers. I have 64-bit sized 64 registers and 32-bit sized registers. The I stands for integers. So the base ICs essentially work on load, store, addition, subtraction of basic integers around. You don't have decimals, you don't have floating point in this base model. The E stands for embedded. Okay. In embedded systems, we know we want to reduce this area, we want to reduce the space, we want to reduce memory, right? Essentially, everything should be small. So instead of 32 registers, you are like, I don't need that much. I mean, I shouldn't use that much in embeddeds. So you have the 16 registers variant. So instead of 32 registers, you have 16. So it's 32-bit, 16 registers. The E stands for embedded. Okay. So this is essentially the base ISAs. And depending on what your requirements are, like I said, you can add on extensions with the multitude of extensions that are available. In fact, there's like so much details and so much extensions to look for in the RISC-V International website. Here I've just listed very few basic ones. I think so far is enough for us. So M stands for multiplication division, and I'll get back to atomics in a bit. F and D is single precision and double precision floating point numbers, like we learned according to the IEEE representation. And vector works on data which keeps using the maybe essentially the same instruction over and over again, like in arrays. For example, let's just say you have two arrays and you want to add the elements with the same indexes. Okay, so like the array one in element at 0 and array 2 element at 0, you want to add them up. Normally what would happen is you take element from 0 from both the arrays, add it, move on, take it from 1, add it, move on, take it from 3, add it, move on, so on. But that's a little time consuming, right? You'll have to, there's so many steps to it. And remember that RISC-V is essentially only load store architecture. That means I work everything only with registers. I have to go to the memory, fetch everything one by one, add it, and then put it back in register and then take it back to the memory again. It's very time consuming. So vectors extensions has this concept of SIMD. Maybe let me write it down. Okay, my handwriting is bad, forgive me. SIMD. This stands for single instruction multiple data. So you are essentially repeating that single instruction over a multiple data values, right? So it's saying I have a single instruction which can work on multiple data. So why not just process all of it parallelly? So instead of doing the addition for 0 first and then 1 first and then 2 first, I parallelly add all of the elements at the same time. So the addition of the values at 0, addition of values at 1, 2, 3, so on happens simultaneously. So you get the values parallelly. So that happens with the vector instructions. And compressed stands for, earlier we looked at the E extension, which is like for embedded systems, instead of 32 registers, I'm using 16 registers. Here, compressed, instead of the usual 32 sized registers, you have 32 sized instruction per se, you have 16 bit sized instructions. So you're compressing the instruction size itself. Again, it's usually used in embedded systems because space. And atomics, I wanted to come at the last for a very specific reason. We have different instructions in certain instructions which happen as fetch, decode, execute, fetch, decode, execute. But we have also learned of interrupts where this instruction or this program is happening and I want to interrupt it for say something. Maybe I just want to give an external interrupt. I want to do anything. That's possible, right? But there are certain programs where I don't want to risk even minutely letting some interrupt happen. So atomics take care of that. It makes sure that the read, write, modify happens at one go. So you don't have the chance to come and give an interrupt. So that's what atomic instructions does. So what makes RISC-V ISA modular is, like I said, you have a base instruction set. So you're not essentially wasting so much space or memory with unrequired instructions you don't need. And depending on what you want, you add so forth. This convention tells you the different extensions you've added to it. RV stands for RISC-V. Followed up is the size of the register itself. And the letters here tell you what instructions you've added to it. So, and another one I want to say is X stands for custom instructions. So, RISC-V also gives you the freedom of saying, irrespective of so much variety of instructions you have, I want something niche to my own domain, which you can choose to add on. So, the X stands for you've used custom instructions. And this is RISC-V architecture's privilege hierarchy. So you have your computers, right? You have your operating system, you have your BIOS, and you have your downloads, your files. But there are certain things in your computer you're not allowed to access because you shouldn't be able to tweak or hinder it. Because if you change something per se, maybe the laptop might crash, or you can't go and tweak the operating system because it's out of your bounds. So this privilege is the tier list of how much control I have over this instruction set. Okay, there are three modes to it. U mode, let me write it, maybe there's U mode, S mode, and M. U stands for user mode, the base instruction set that we looked at, and maybe adding on different instruction sets. You can use the add, subtract, multiply, division instructions itself like a normal user. S stands for supervisor mode, which goes beyond the normal instruction set with extensions you have. You also have this virtual memory access. And machine mode is like the top tier mode with hardware level control. So RISC-V divided into non-privileged and privileged depending on the control you are given, because you want privacy, you want security. So let's have a recap or like a preview of the standard extensions. M is for multiplication, division, and atomic instructions are read, write, modify that happens at one go. So you don't, no other processor or no other thread can sort of interrupt what is going on. F is for single precision, which is 32-bit. Double precision is D for 64-bit. There is also Q, which is for quad precision, which is 128 bits, but I don't think we need that. Compressed instructions is C. You're compressing the 32-bit instructions to 16. Vector, like I said, uses single instruction, multiple data, parallel processing because it's easier and rather less time consuming. And if you look at it, the multiplication, this floating decimals and atomic, all of these are something I would usually normally want, right? I mean, I can't just be stuck with addition and subtraction. So you see all of these bundled together always. So rather than, writing it like huge profile, we use G to represent the integer, multiplication, atomic, all of these instructions put together generally. And this ZICSR, ZI is comes under the ZI instructions. The FENSI is used for memory modeling and also in atomic instructions about which order of instructions can you allow to be reordered for efficient processing. But that's not in syllabus, so let's just, I mean, if you guys are curious, it's in the website to look forward, but it's just another instruction, that's all. Extendable. So RISC-V, like I said, base model extensions. So whatever domain, whatever you want, you can put it to that specific use case for, say, AI, machine learning, security, and embedded systems. We have something very niche to embedded systems itself, right? The C and the E instructions. And vector, we have the vector instructions. And research, so let's say in math and physics, you want some accurate data and statistics and so on. You have the multiple precision points available depending on F, D, or Q. And this is essentially the different domains in which RISC-V is being used. Right now, you see there's a rise in the use case of RISC-V because it seems much more faster, right? and load store architecture. So RISC-V is mapped on this full concept of not being able to directly access memory. So if you look at the normal CISC architecture, which is complex instruction set, you we have looked at the different addressing modes, right? Let's just say you want to add two numbers. You can do so by having one number in the register and then going to the memory and fetching it. That is possible in just one instruction. You don't have you it's implied that you have to go to the memory and get it. But in RISC-V, it's always every process, everything is only within the registers itself. So even if the data is in the memory, you first bring it to the registers, you add it in the registers, and then you maybe put it back to the data. This makes things much easier to process in the CPU level, and also it makes pipelining easier. So let's just look at maybe add brackets 1234H comma 5465H. Let it be a random address. Essentially, what is this instruction saying? I have to add two values, but they are in two different memory locations. So first, I have to decode this, and then I have to go fetch the values in these two memories, and then I have to add it, and again I have to put it back in one of the memory locations. Although the instruction itself seems pretty intuitive and small for us humans, it's long, it's time consuming because you have to go through a huge process. And during a pipeline stage, when this happens, the pipelining time, like we look, depends on the longest stage, right? So irrespective of how small this instruction looks, this is time consuming, right? But imagine if all of it was in registers itself. You have no problem of locating where it is. You have the registers, so you just add them up and then you get the value. So it makes pipelining much faster and makes each stages almost equivalent in time. And so that's the essence of RISC-V architecture. You only have load and store, loading it from the main memory and storing it back to the main memory, and ALU does all the operations, and then you put it back into the memory via the registers. So just one more thing in case anyone's confused. So you have 32 registers, right? So the first one is always hardwired to 0, and depending on whatever use case you have, the X naught takes some values. I think it will be covered later by Nagadarshan. So this is all pretty much, guys. Let's have a RISC-V at a glance. It's open sourced, completely free, don't have to pay a licensing fee. Modular, you have a base ISA, and depending on your needs, you had extensions. Extendable, you tailor to whatever needs you have. Only load store, so makes pipelining easier, makes processing much faster. And so I hope it was understandable, and thank you guys. All the best for Ensigns.
So hi guys, now we'll be seeing about the RISC-V instructions and the instruction set basically. So till now we have saw about what is RISC-V and its features etc. So now we'll be seeing about the major instruction set and also the register set of RISC-V architecture. Moving on to the base integer instruction set, which is the core set of instructions, which is the foundation for the RISC-V architecture, where RB32I, RB64I, and RB128I stands for this integer instruction. And the main aim is to use minimum number of instructions needed to build everything else. So in our case, we have a fixed instruction length of mainly 32-bit, which is 4 bytes, and fewer instructions, powerful to run real programs, foundation necessary stuff, simple, fast, and efficient design. This enables easier decoding, faster execution, simpler hardware design, and sequencing. The main feature of RISC-V architecture is the load store architecture, where only these two instructions, load and store, can only access memory, while all the other instructions must be handled within the registers. And also, the instruction length is fixed such that This makes the RISC-V architecture or the RISC architecture more efficient. That is, there is no direct memory arithmetic, we can say, and all computation is done in registers. Moving on to why 32 bits. So this is basically not a random number. It is optimized for a larger hardware, more power, and slightly longer process as well. And it is correct for opcode, can also be used for three address, like three registers instruction, can also be used for immediate values, and it's also scalable. So if we consider it as 16-bit, we cannot use like three address mode. Also 16 registers, each register would have to have 4 bits. So that is actually not possible. So for also a low cost embedded system, we have a subset of RB32I, which is RB32E, which has 16 registers in it, which is used for purposes like microcontrol, sensor, battery power system, etc. Coming to the basic instruction formats, how will an instruction for RISC-V look like? So basically, we'll be dealing with source and destination registers, and the main feature of instruction is the opcode, which is actually 7-bit in RISC-V, which says what type of instruction it is. So basically, there are 6 types of instructions, and it is this opcode which says what type of instruction it is. RD is destination register, which is stored in address bit of 5 bits. Then RS1 and RS2 are source registers. Func3 and Func7 are basically 3-bit and 7-bit function determiners, we can say, respectively, where they decide in this type of instruction what operation is being done. That is being decided by Func3 and Func7. And immediate values are also used to give the value directly in the instructions. So this is the basic instruction format we can see. Here it is the Func7, RS2, RS1, Func3, RD and opcode. And we can say in total, this would for sure make 32-bit instruction. 7 plus 7, 14, 14 plus 10, 24, 24 plus 8, 32-bit instructions. Coming to immediate values. So we basically have these immediate values, which will be in 12 bits or 20 bits. But the value in registers are 32 bits. So how will these immediate values be added or subtracted with the registers? There comes the concept of sign extension, where we'll be having a 12-bit immediate value or 20-bit immediate value. We'll be seeing the MSB. And suppose if it is 0, we'll add zeros to all the previous bits. If it is 1, we'll add 1 to all the previous bits. So this is a major feature of immediates. Then splitting, in the sense, in the instruction we split the immediate value, like it will be, if it is 12 bits, it will be in 2 parts. So this enables a quicker and a easier and a main modular access by the processor. And different, what do they mean by different formats? In the sense, we have various types of instructions which we'll be seeing in detail later. Coming to instruction categories, there are majorly 6 types divided into these 3 groups. One is computation instruction, ALU operation, load store instruction, and control flow. Computation instructions are the instructions where we'll do the basic operations like register operations, immediate operations, and load store architecture. Coming to control transfer, we have the branch and jump instructions, where these are used to like do a loop in a single program as well. We also have a special immediate instruction U type, and all these type which we'll be seeing in detail in few minutes as well. And these are the basic 6 types we can say, and thus we'll be seeing each of them in detail and what is the purpose of it. Coming to other categories other than the main 6 categories, we have fence instructions, system instructions, and hint instructions. Coming to fence instructions, memory ordering, the order device input, output, and memory access as viewed by hearts and external devices. So these are the orders of any combination of input, output, read, and write. Coming to system instructions, these are basically the equal environmental call and breakpoint instruction which is being used. And finally, hint instructions provide performance hints to hardware. So the overall flow execution in RB32I include, like we have the first is load, where we'll get data from the memory, then compute from the ALU operations, then store right back to memory, and then control flow, which is used in case if needed. So basically this is all about the execution flow. Now we'll be moving on to the register set and instruction set in detail. So RISC-V architecture. It has a register file of 32 registers, X0 to X31, which is the notation being used. The 6 core instruction formats: R type, I type, S type, B type, U type, and J type. And how these combine to form one of the most elegant ISAs in modern computer architecture is what we are going to see now. Coming to the instruction set, there are basically 32 general purpose registers in RB32I, which means there are 32 registers and each of 32 bits. So always this 32 registers will be fixed. The number of bits which is stored, the data which is stored only varies to 32, 64, 128, etc. And there comes the name RB32I. Each bit is 32 bits. So getting into the detail of the registers, first comes X0, which is the first X0 register, and that is hardwired to 0. So this guards results and supplies 0 operands and cannot be rewritten. So X0 always has a hard code value to 0, and such that it can be used anywhere, like whenever we want 0. Moving on to next registers, while X1 to X31, they serve for data addressing and calling convention roles. So as I said, X0 is mainly for hardwired value or immediate value of 0. Coming to X1 and X4, they are the special type of registers, where X1 is the return address, X2 is the stack pointer, X3 is the global pointer, and X4 is the thread pointer. So return address, in the sense, X1 stores the return address, stack pointer, it points to the top of the stack. Global pointer, in the sense, it points to the global variables or global function which is being used. And thread pointer, in the sense, it is similar to the linked list, where this thread pointer will point to the current value. So that is basically the use of these special case registers. Next comes X5, X7, and X28, X31, which are the temporary registers. So another notation for these is T0 to T2 and T3 to T6. So totally there are 7 temporary registers, and these are called as caller save temporaries. Also we have X5, which acts as an alternate link register as well. Coming to X8 and X9 and X18 to X27, these are known as saved registers, where these are called as callee saved registers preserved across calls. And we have S0, which is actually X8, which also acts as a frame pointer in this register set. Frame pointer, in the sense, it points to, suppose we have a stack knight, points to the current frame which is in place which we are dealing with. So that is the use of the frame pointer. So difference between caller and callee saved is that, assume you have function A and you have function B. So function A calls function B, then function A is caller and function B is callee. So all the registers which are being used by the caller function A are known as temporary registers, and the registers which are used by the callee, that is B function, are known as the saved registers. Now finally, coming to one of the most important set of registers in this entire set is X10 to X17, which is A0 to A7, which are argument and return value registers. So A0 and A1 usually holds the return value, and A0 to A7 can pass up to 8 arguments. So this is the major register which we'll be using in most of the operations in this course here. So basically X10 to X17 are the main registers which we'll be using. So we can see in the table, X0 is 0, X1 is return address, X2 stack pointer, and X8 frame pointer, etc. So this is the basic register set in this RISC-V architecture. And the main registers which we'll be using is A0 to A7 and then X0. Let's move on to RISC-V instruction formats now. So every instruction is basically 32 bits wide, enabling predictable decode logic and simpler hardware pipelines. So basically, in RISC-V, we have 6 types of instructions. And it is the opcode which determines what type of instruction it is. Assume we have instruction coming from memory to the processor. How will the processor identify what instruction it is? It is based on the 7-bit opcode out of the 32-bit, and that decides which type of instruction it is from these 6 types, and what function is determined by the func3 and func7 bits. So first type is R type, where it is a register to register operator instruction. Next is the I type, where it is the immediate arithmetic instruction. Next S is store type. B will be used for conditional branches. U is for upper immediate, and J is for unconditional jump and link, which we'll be seeing all of these in detail. So all 6 formats share the same 7-bit opcode, ensuring the decoder always knows the format before reading any other field. So this is the main aim of opcode which we'll be using in this chapter. Coming to the first type, R-type instructions, register to register operations. Before getting into the detail, let's see this example. Add x10, x11, x12. So what does this mean? Add the values in x10, x11 and x12 and store the result in x10. So this is the basic instruction which we are seeing in which we are dealing with throughout this course. So opcode. So before getting into detail, for this instruction, we know this instruction is 32 bits. But how is this 32 bits printed and how it is working? On seeing that in detail, we have 7 bits which is for opcode. And the opcode for R-type instructions is 0110011. So it is with the help of this opcode, the processor decides it is R-type instruction. Next, we have RS2, RS1 and RD, where this is the source register 1, source register 2 and destination register, each of 5-bit address. So here X11 and X12 are source registers and X10 is said to be the destination register. Coming to func7 and func3, it determines which operation, addition or subtraction or XOR operation, which operation is done. That is being determined by func7 and func3 bits. So basically opcode is to say what type of instruction. RS1 and RS2 or RD are 3 registers, and func7 and func3 is used to say what operation is exactly done. It selects the exact operation. So RD destination register, and these determine type of operation, and RS1 and RS2. So here we can see func3 and func7. When all are 0, it will be addition. And when func7 is this one, it will be subtraction, and XOR, this will be different, and operation, this will be different, and XLL operation 001. So this will be the difference. So this is how the processor decodes the instruction. Like the opcode is this, so R type, and then func3 and func7 is this, so addition, and then these registers. So this is basically all about the R type instructions. Moving on to next type of instructions, it is immediate operation and loads. So basically here we'll be having a 12 signed bit immediate, and we'll be directly performing operations along with this with a register. So they cover immediate arithmetic, logical shifts, and all load operations as well. So coming to this example, add I x10, x11, 5. So what does this mean? We add a 5 to the x11 value and then we'll be adding it to x10. So add I in the sense whenever we deal with immediate values, we'll have this letter I. So x10, x11, 5 in the sense add x11 plus 5 and then put it in x10. So this is the basic meaning of this immediate arithmetic instruction. So coming to the opcode, here also we have a 7-bit opcode which tells the processor that it is I-type instruction. Now coming to, we have a single source register here which is x11. And we have a single destination register here which is x10. And then the immediate value 12 bits. And here we only have func3 which is 3 bits which determine what type of operation. So in this case, the func7 and RS2 is combined to form the immediate bits, giving a total of 32 bits. So opcode is this one, RD and RS1 is this one, and immediate value is 12 bits signed external immediate decimal 5. So here, okay, So we know that the value in RS1 will be a 32-bit value, but this immediate value is just 12 bits. So here is where we use the concept of sign extension, which we saw before for dealing with immediate values. Coming to the second subtype of this I-type instruction, which is the load word type of instructions. So LW extend comma 8x11. So load, what does load mean? Load means in the sense we'll be taking a value from the memory and we'll be storing it in the register. While store in the sense we'll be taking value in the register and we'll store in the memory. So what is load? We are taking value from the memory for using. So a value is taken from the memory and we'll store in a register. So load word extend comma 8 into x11 where 8 is the offset. So we are simply saying x10 is equal to the memory of 11x plus 8. I mean like x11 plus 8. So we'll first add x11 plus 8 and what is there in that memory we'll be giving it to x10. This is the basic aim of load word instruction and load architecture. And the opcode for this one is said to be this, which determines it is I-type instruction. And since I-type is divided into two subtypes, both will have different opcode to determine which type it is. And here we also have func3 010, which is for load word it is 010. For load byte it is 000 and load half it is 001, which determines what type of load we are doing. And immediate value here is just 8, which we are acting as which acts as an offset that adds to the RS1 register. So this is basically all about the I-type instructions. So we have two types. One is directly adding immediate value, and one will use the immediate value as an offset to go to the memory, and then that value will be loaded in the register. Next, coming to S-type, where it is the direct opposite of L-type instruction, which is store operations. Coming to instruction, store word, SW in the sense store word, x10, 8, x11. What does this mean? We have to store a value in a register to the memory. So store word x10, 8, x11 in the sense, we'll take the value from the x10 register and we'll be storing it in the memory of x11 plus 8. Store the 32-bit word in x10 to the memory address x11 plus 8. And the opcode for this type of instruction is this one. And here we have RS1. Like here we have RS1 and RS2. We do not have a destination register because the value is stored in memory. So RS1 is basically said to be like x11 and RS2 is said to be x10, where they have the data which is used appropriately. And then here we also have the immediate value, which is 12-bit immediate. But this is being split into 7 bits and 5 bits. Why? Why in the sense the processor always knows that RS2, RS1 and opcode, these will be fixed. Like whenever opcode is an instruction, it will always be in the last 7 bits. So the processor always knows whenever opcode is present in an instruction, that will always be in the last 7 bits. Whenever RS1 is present in an instruction, it will always be in the third part of 5 bits. Whenever RS2 is present in the instruction, it will always be in the second part of the 5 bits. So what if we put this immediate value here and shift all these? The processor will get confused. So whenever we are using a particular feature in an instruction, we have to give it that place such that the processor easily identifies, and we can fill the remaining places by splitting the immediate value, etc. as we need. So that is the reason this immediate value is being split into 7 and 5 bits. This is about the store operation. And coming to store bit, store off, and store word, we have the func3 which determines which of these is done 000, 001, and 010. It's 8-bit byte, 16-bit half, and 32-bit word. So basically, about store operation, there is no destination register. We'll take a value from the register and we'll store it in the memory of the register plus offset which we are using. This is all about the S-type instructions. Moving on to B-type, where they are the conditional branch operations. Coming to this example,
So, hello, I'm Harish, and for this session, we'll be looking through load store architecture and common instruction categories for RISC-V. So, to start off, we'll discuss through why this topic is required. And in terms of an exam perspective, direct theory questions may be asked, but I would say this session would be more useful for understanding the intention behind the load store architecture so that we can compare, you know, load store architecture and ISAs that don't use load store architecture, see where this one has its benefits compared to the alternative, and see where the alternative has benefits compared to load store architecture to essentially get the idea behind why we implemented all of this so that when answering other questions from this unit, you can answer with a bit more confidence as to why a certain thing is the way it is, right? So load store architecture is a design choice essentially that we'll be looking into. Okay. So what is load store architecture? Load store architecture is where only a only certain specific instructions have access to the memory, right? So compared to, let's say, CISC, okay? CISC doesn't use load store architecture, and there are basic commands that have access to memory. For example, the addition of two numbers. If you want to add two values A and B, and I want to store it in A, all I have to do is add A, B, and my compiler will be able to take the value from B and add it to A. And now this instruction, the simple instruction, had to use the memory, one for fetching from B, and then it had to write into A plus B, right? So that's memory operations. And there are multiple such instructions that will all use memory. That'll all, interact with the memory. Whereas in load store architecture, your regular commands will not be able to touch the memory. Instead, you see these two, right? There's load and there's store. These two instructions will be the only ones that are allowed to touch the main memory. Okay. Now, if a command does require information from the memory, what we'll do is we'll take that information with the load command and we'll put it in a register. Okay. And when we want to process that information, we'll take it from those registers. We'll do whatever manipulation we want, and we'll put that manipulated value back in some register. And if you want to store it in the main memory, you'll have to use the store command to put that value back into the main memory, right? So registers will act as the interface for all memory, and load store are the two commands that will be used to go back and forth to take stuff from the main memory, put it into the registers, and the alternative as well. So no other command will have access to the memory. Okay. And again, the key ideas is the same thing. The reason we're doing this is to separate memory access and separate computation. Okay, so I think we can visualize the difference. I mean, what do I say? The benefit of such separation with an example, right? So let's take two different cases. It's a workspace. Okay. Um, let's say that I have two restaurants, and there's a chef in one restaurant. Let's call the restaurant one is the non-load store restaurant. Here I have a chef who does everything. Now the chef, he'll get an instruction saying, "Hey, make a sandwich, make a certain sandwich, and deliver it to table 3." Right? Now this chef will get the instruction. He'll decide what he needs to make that sandwich. So he'll go all the way to the pantry. He'll get the bread. He'll get the required vegetables. He'll get the, everything required for that sandwich. He'll come back to the counter. He'll do his cooking work, and then he'll go to the tables outside, he'd go serve the food, and then he'd come back, and then he'd do the next instruction. This would be the CISC equivalent, let's say. Now the load store architecture equivalent would be, instead of having one chef, you would have a specialized team of people. Okay, you won't have just one person doing the cooking and the same person serving the food and the same person getting food from the pantry. Instead, you would have multiple people, and each of them are specialized. Okay, the chef in the load store architecture, what he can only cook whatever ingredients are placed on the counter. Now this chef doesn't have the capability to move. Okay, and there are also two different other people. One guy, is simply for getting stuff from the pantry for the chef to cook with. And the other guy will take whatever the chef is cooking and he'll go provide it to those tables, right? Now, both of these running people don't know how to cook, and the chef does not know how to run either. Okay, it's kind of like you're taking the chef from Sisk and you're splitting him in based on his functions, right? I hope that makes sense. So now we'll see the essential difference we are producing by between these two systems. Okay. The first difference would be the memory accessing. Because let's say that in terms of the chef example, the pantry is part of the memory, and the tables you're serving is also some part of the memory, kind of like loading and storing, right? Now the chef does absolutely everything, right? If he wants to make a sandwich, he has to go all the way to the pantry. He'll come back. He'll go all the way to the tables, and then he'll come back. But here in how do I say, in load store architecture, he doesn't have to do all that. The chef, all he does is take stuff from the counter, cooks it, right? And two very different people are the ones that go access the memory. So I hope the analogy is clear here. The counters are in a way the registers, right? Because the chef only works with the registers, and only two different people have access to the main memory, being the load and store, right? Everything else is done with information on the registers. Okay. Now the second difference that I hope everyone realized is that there'll be a difference in the way you give your instructions. To the Sisk chef, you can say, "Oh, just make me a sandwich, give it to table three," right? That's all I have to do. Now this chef will understand that he has to make a sandwich, and he'll understand what is required for that sandwich. He'll make it and he'll go give it. But for load store architecture, since there are three people, you would have to give different instructions to each of those people. To the guy who has to go to the pantry, you'll say, "Get me bread, get me, I don't know, butter, vegetables, all of that, and put it on this place in the counter." And to the chef, you'll say, "There, when you get those components, when those items are there in this part of the counter, you take them, you assemble the sandwich, and you keep it at a different part of the counter." Okay. And to the serving person, you tell him, "Okay, these components will be on the table. All you have to do is take them and go give it to table three." So the difference here is that you'd have to split your instructions up. And if you noticed, each instruction was a little more detailed compared to Sisk, right? So that was back in the days one of the benefits of Sisk, because memory was very expensive. They didn't want to spend more and more information on memory. So what they did was they made sure their instructions itself were very small, but the decoding part of Sisk was quite difficult. Okay, the chef has to be really smart, right? He has to remember every single recipe. Given a recipe, he has to know what he has to go take from the pantry and all that. So Sisk was a bit more complex in terms of the hardware, but in terms of memory usage for the instructions, it was quite small. In Risk, on the other hand, the hardware part wasn't much of an issue, but the instructions took quite a bit more memory, right? I hope that makes sense. Since each part is specialized for one task, the hardware complexity goes down by some extent. The next step, the next difference between Loadster and its alternatives is the fact that you can pipeline in Loadster much easier. This is because each instruction in Risk or in load store is much more fundamental compared to Sisk. Okay, Sisk instructions are quite rigid. Okay, you have instructions like make this recipe and serve it to this table, or make that recipe and serve it to this table. But if you noticed in Risk, to each person you gave a much smaller instruction, right? And you gave much more of those small instructions. So if I split that task into smaller instructions, that is essentially creating a bigger pipelining depth. Okay. And as we all know, more the pipelining depth, the faster your pipeline actually gets. Okay. If it makes sense, since three people are doing tasks now instead of one, in load store, since three people are doing tasks, those three people can overlap the tasks more efficiently compared to Sisk. Okay, since there's only one person, if he's working on a sandwich, he has to finish making that entire sandwich. He has to go to the pantry, get the bread, all of that. He has to do everything, and only then will he move on to the next instruction, which is, let's say, bake a cake for this person. Right? So he has to finish the sandwich and then go to the cake. But in load store architecture, let's say that the runner who goes to the pantry has gone to get the food for the first what's it called, the first dish, right? But the chef can see that the ingredients for the next dish is already on the counter. He can start working on that while the runner has gone. And again, they can all work independently, right? They can work to some extent, they can work independently. And the fourth point is actually a continuation of the third point. Okay, optimization can be done with pipelining. So instead of going linearly for with tasks, you don't have to go, like, let's say I have make a sandwich, bake a cake, and make some other dish. I don't know, fried rice or something. Okay, in Cisc you would go linearly, right? You'd finish that one big task, which is making a sandwich, and then you'd finish the next big task, that is baking a cake, and then you'd finish the next big task, which is making the fried rice. Okay, but in load store architecture, I don't have to do that parallelly since I'm pipelining. Whenever I have gaps in the middle, because let's say the chef will be idle in the first instruction when the runner has gone to get the items for the sandwich, right? When he's getting the bread, the chef will be idle. There will be similar cases where the chef is idle or where the waiter is idle, or so on and so forth. In those idle cases, I can smartly do some optimization, and I can say, oh, I have the ingredients for making this sub part of my dish. Therefore, I'll start working on that. Now, those kind of optimizations get much easier in load store than in its alternatives. So one thing I want to mention is that load store architecture usually always corresponds to risk. This is because when you follow load store architecture, you will automatically, to some extent, follow all the design principles of risk as well. Okay, and the other way around works as well. Any kind of risk implementation always uses load store architecture. Now, some examples of risk implementations are ARM, ARM, which is Advanced Risk Machines, and RISC-V, right? Both of them use load store architecture. So whenever you use load store architecture, you can feel free to think about risk immediately, and vice versa as well. Okay, so this is the main, what do I say? This is the main benefit of load store architecture, because, as I said, pipelining and optimization exist, right? These two speed up our processes a lot. Our processes are done much quicker and much more efficiently, right? Now we'll move on to common instruction categories. Now this is, how do I say, a more memorization oriented thing, not much to understand per se. It's a really easy topic, so we'll skim through it quickly. These are the kinds of instructions we have, which is data transfer arithmetic, logical bitwise, shift rotate, control flow, compare and set, immediate, special and system. Okay, we won't look through most of these. The blue ones, right, which are data transfer, arithmetic, logical bitwise, and control flow. These were what were highlighted in our portion. And the rest, I mean, I think it would still be beneficial for everyone to go look at it. It'll take, like, I don't know, 2 minutes per subtopic, right? These are, again, really, really easy to understand. So I don't know, have a conversation with some sort of AI or anything, or maybe Google it a bit. I hope you'll find it interesting as well. Okay, I would, like, just in case if it may be asked, but we will be looking mostly at the blue ones. Even the blue ones are easy. The black ones are like uh, not immediately intuitive, but they're worth looking through, right? So first we have data transfer. Again, these are the commands that will move the memory from the main memory to the registers. Okay, they'll move values from the main memory to registers and vice versa. Okay, those are load and store. Load is used to take values from the main memory, put it in a register for some other command to work on it. Store will take the value from the register and store it into the main memory. These are, I hope, really easy to understand. Arithmetic performs basic mathematical operations and it operates on register values. Okay, so these assembly instructions, what they do is they'll take, let's, those specific values from the register. They'll do the manipulation required, addition, subtraction, multiplication, division, any one of them, and that value that was, let's say, divided or multiplied or added or subtracted, that value will again go back to the registers. Okay. um that's what it means. That's what operates on registers means. Okay. This is quite important. I hope everyone has this in mind, right? Load store architecture, any kind of operation other than load and store can only access registers. Everything is done via registers. Okay. We have logical and bitwise next. This performs operations at the bit level. Okay, logical operations, I'm pretty sure we've all studied in some subject or the other, right? And or XOR not. This is again, it'll take two different values and do the certain comparison, and its output will be stored in a register. Okay, used for masking and data manipulation. Yeah, it is a see. We can check what this means on our own. I mean, I do not think it is very necessary, but just in case if you feel like you should know, then you can. Okay. And control flow finally. Okay. So for this, for IoT students, I'm pretty sure we've done 8086 and 8051, right? So we know what a control flow branch or jump means. But for those who don't, I'll also explain. Okay, let's say we have an assembly code. Okay, I have some sort of assembly code. I mean, pretend that these lines are the syntax. Okay. Now, assembly doesn't have properly defined loops. Like in high level languages, we have things like while loops and for loops and all of that, right? Now, in assembly, there isn't a if else, there isn't a loop or anything. What we have instead are branch and jump statements. Okay, what these will do, they can help you jump back to a certain line based on that line's address. Okay, based on a certain if that condition triggers, it'll push you back to this line. And I hope we're able to see how this can function as a loop, right? So changes execution order of instructions. Given I have these instructions, I can jump from this instruction to this instruction based on some certain conditions. Those conditions are usually based on flag values. Okay, what flag values are certain triggers. How do I explain? It's like when a certain condition is met, when certain things happen, there are these registers called flags that will get triggered, okay? And depending on the value of the flag, these branch and jump statements will take you back to this line of the code, okay? So, for example, let's take BEQ as an example. What this means is branch if equal, right? Branch if equal means go to this line if A is equal to B. Okay. If A is equal to B, so you see how this works like an if else loop, right? If A is equal to B, then branch. BNE means branch not equal. It's basically the same thing, except for there should be a negation in the front, Mary. Okay. There'll be a branch that occurs if those values are not equal. Jump just says, okay, just jump to this line of the code. Okay. Usually there'll be jump and some value. Okay. And that value will be the address of the line. I hope that makes sense. Okay. So again, from an exam point of view, this is all just theory, but I would rather have everyone understand what everything means so that you can answer other questions confidently with the understanding behind why load store architecture and again the purpose of these certain instructions. The best way to utilize this video and the best way to learn whatever I've taught is to again probably use AI to have a conversation on what you interpreted from this and maybe go through do some troubleshooting and some amount of verification. At best it'll take about I don't know, 10 to 15 minutes. That's all it took me to learn. Maybe like 10 to 20 minutes it took to learn all of this. I guess I did take quite a lot of time to explain it, but hopefully it makes sense, right? Maybe try coming up with your own analogies on how everything works. That is all for this chapter. Thank you for listening.
Okay. Hi everyone, I'm Anjan and I'll be taking care of the last part of Unit 5 in our COA course. I'll be talking about the evolution and comparison of instruction set architectures. This will be a pretty short discussion, but yeah. So we will be looking at the evolution, the different types of ISAs,
the comparison of the most dominant modern ISAs, and very specifically the different advantages and limitations of RISC-V. And finally, we'll just have like a quick look at the different ISAs that were made for very specific use cases. Now, just a quick recap. What is an ISA? An ISA, very simply, is like an interface between software and hardware. So it's like a very specific set of instructions that a CPU would understand. And based on that, it can define what a processor can do and the method by which it does it. So beyond this, you can also define like how the registers, like the internal storage would be accessed or how they'll move around. You can define like data types, addressing modes, and like any specific instruction format. So this is what an ISA is. Now, when we look at its evolution, initially we just didn't have any ISA. We never had like a set uniform system. We had how to put this? So each computer would have like a very specific set of code, and if you use this code anywhere else, it just wouldn't work. So obviously, this is very redundant and time consuming, right? So to fix this, we developed CISC. CISC stands for Complex Instruction Set Computing. Now, it was a powerful and very complex instruction set where a single instruction could like trigger multiple operations. Now, since it was so complex, fewer instructions were done per task. But this also meant that the hardware had to be equally complex and the entire system was a bit slow. So, normally, when we have something slow and complex, we would want to make it simpler, right? So, that's why we came up with RISC. RISC stands for Reduced Instruction Set Computing. So, it's much faster, simpler, and more power efficient. But for each process, you would need to have a bunch of lines of code. But the thing is, initially, RISC was proprietary, which meant that only certain people could use it after paying some fee. And this also meant that customization was pretty limited because the initial versions of RISC was called ARM, and that was made for embedded systems and mobiles very specifically. So naturally, to fix this, we came up with modern open source ISAs like RISC-V. So RISC-V in specific is open source and it's free to use. And since it's open source and very versatile, it's free to be modified. And since it's new and all these like since it's free, as I mentioned before, it has sparked like rapid innovation. So a lot of people are coming up with a lot of new things. And since it's customizable, it's really widely used, especially in newer systems. Now, when we look at CISC, initially we had Intel x86, which was the most dominant ISA. We also had, I mean, even if you look at it now, we still do have a lot of systems following Intel x86. ARM, we will normally see it in our mobile phones and embedded systems, as I mentioned before. And RISC-V is emerging, but yeah, this is a general evolution. Now, when we look at the different ISAs, they're very clearly split into CISCs and RISC. Now, just as a recap, CISC is powerful, complex instructions. You have one instruction, multiple operations, or even just one entire function. Now, this also means fewer instructions per task. But because this is so complex, you needed equally complex hardware, which made it slow. And since this was more hardware dependent, it was also costlier. But when you look at RISC, it's simpler and more basic instructions, very fast, but you need multiple instructions for one operation. Now, it was easier to optimize and design, and it had more registers and more control. And RISC tended to be a more software dependent system, which also feeds into why it was more easy to design and optimize, right? Now, the modern major ISAs, as I mentioned before, were RISC-V, ARM, and x86. So when we compare them overall, we have, based on hardware design and complexity, x86 was the highest complexity because it is a CISC architecture. After that, we had ARM and RISC. When we talk about complexity and flexibility, RISC-V is definitely the most customizable. ARM was limited in certain cases. As I mentioned before, you had to pay and get certain permissions. And then x86 was very limited. And then when we talk about usage and power efficiency, since RISC-V is more software oriented, it took much less power. And ARM was also very efficient. In fact, even more efficient than RISC-V because it was focused, like when they created ARM, they were more focused on mobiles and embedded systems. So it is highly power efficient. And then CISC's Intel x86 was very bad with power efficiency as it was hardware heavy. Now, this is like a general comparison table. If you look at this here, essentially done with the comparisons. Pretty self-explanatory. Just remember, ARM was made for a specific use case. So in certain areas, namely the power efficiency, it's better. Otherwise, it's generally medium. When you look at RISC-V, it's like ideal all across the board. And then when we look at x86, it's not that ideal. Why? It's RISC, and the other two are, one, why is Intel bad? It's CISC and everything else is RISC. So just remember that. And then when we look at the advantages and disadvantages of RISC-V, RISC-V, since it's like open source, it's really customizable, right? So it allows like rapid innovation and like creation of custom processors. So like if someone comes up with a new system, they would prefer to use RISC-V. But since it is a new software, it has like a smaller ecosystem that has been researched and it has limited support as well. But its performance is improving, and this necessarily need not be a disadvantage. It just means that there's like a lot more space in the market. But this is generally the advantages and disadvantages of RISC-V. And finally, we've come to like the different ISAs. This is not necessary, sir said that we do not need to know this, but it's interesting, I guess. Very specifically for IoT, I would say just keep AVR in mind. So AVRs are used for the ESPs and Arduinos and like the edge embedded stuff as well. So that would be important to us in the future. And then VLIW stands for very long instruction word. So it's mainly used in digital signal processors. That's also something we might need to know. But besides that, you don't need to know this slide. But yeah, we are done. To conclude, ISAs, first we had no ISAs, then we went to a very complex instruction set, which wasn't that customizable called CISC. Then we made to a much simpler form called RISC, but initially it was proprietary. But now we have something called RISC-V, which is open source, very flexible, power, and it's free for everyone. Now, when we look at its advantages, it's flexible and open, available to all. And its disadvantages would be simply the fact that it hasn't been researched enough as it's new and emerging. And since Intel x86 is still pretty dominant, the transition would be a bit rocky. We are in the transition state right now. And yeah, I guess you guys can see this to see the different types of ISAs, but it's not necessary. And we are done. Thank you for listening.